Modeling using trigonometry. Let's compare the motions that are modeled with either the sine or cosine function. The red ball is modeling uniform circular motion. The blue ball is modeling simple harmonic motion. The Earth is a spinning sphere that rotates on its axis once every 24 hours. Because of this, there are numerous applications of sine and cosine functions. The angle of the sun above the horizon during daylight hours is one example. Imagine a pendulum that swings as shown. Let the end of the pendulum be all the way to the right, where x equals 1 at time t equals 0. The next time the pendulum is all the way to the right is at time equal to 2. Sketch below. Alright, so when time equals 0, that's this axis here is t for time, we want our displacement to be at 1, which means it's going to start out like this, and then it's going to go down. At -1, we're all the way over here at time equals 1, and we're at displacement of -1, and then it goes back up, and by time equals 2, we're back up at a displacement of +1. And there we have it. What is the period? Well, that would be 2 seconds, because that's how long it takes for the pattern to start repeating itself again. So if we start right here at this point, we get back to that same point 2 seconds later. The amplitude is from the midline up to a maximum, and we can see that the amplitude is 1. We could also measure it from the midline down to the bottom minimum point here, and that still has an amplitude of 1. The period is 2 seconds, and the amplitude is 1. The period of A times sine of bt plus k and A times cosine of bt plus k is given by period equals 2 pi over the absolute value of b. You can also write it as the absolute value of b equals 2 pi over the period. Note, the absolute value of A is the amplitude and y equals k is the midline. The period of f of t equals 6 sine of 2 pi t over 24 is 24. Its amplitude is 6. True or false? Alright, so here, t is our variable, and everything else surrounding t is our b value, because here we see b times t. So that's 2 pi over 24 is b. That's what's multiplied by t. Now 2 pi over 24 can be simplified to pi over 12. But what we're going to do now is take 2 pi and divide it by b. So 2 pi divided by pi over 12. We could also write that as 2 pi times, and then flip the fraction, 12 over pi. So the pi's cancel, 2 times 12 is 24, and the amplitude is a, which is the number multiplied outside of the sine function, and that is 6. So this one is true. Alright, next. The period of h of t equals 1 minus 7 cosine of 2 pi t over 365 is 365. Its midline is y equals 1. Well, its midline is 1, y equals 1, because that's our k value. So this piece is true. Let's see, if 2 pi times, we're going to take 2 pi over 365 and flip it over. So 365 over 2 pi. So what I've done is taken 2 pi and divided it by b, which is the same thing as multiplying it by 1 over b. 2 pi's cancel. The period is 365. This is true. All right, next. If y of t equals 5 plus 3 sine pi t over 60, the period is 60 and the midline is y equals 5. The midline is 5, y equals 5, because that's our k value. Now here we have 2 pi divided by b, and b is pi over 60. So 2 pi times 60 over pi, I flip the fraction, the pi's cancel, and the period is 120, not 60. So 3 is false. If h of t equals 27 minus 13 cosine pi t over 4, the period is 8 and the amplitude is 13. The amplitude is 13 because that's our a value multiplied out front of the cosine function. And the period is going to be 2 pi divided by b, which is 2 pi times 1 over b. b here is pi over 4, so we multiply by 4 over pi. Pi's cancel, period is 8. 4 is true. True, true, false, and true. A vibrating spring mass system's motion is sinusoidal. The mass at the end of the spring moves up and down along a vertical axis so that its position satisfies y is greater than or equal to -20 and y is less than or equal to -10. Let's imagine that at time t equals 0, the center of the mass is at its equilibrium position where y equals -15 centimeters and is moving upwards, arriving at the maximum position for the first time at t equals 0.1 seconds. What is the period and what is the amplitude? All right, so we start in the middle. So here's 15, and it goes all the way down to 20, and it stops up here at 10. So it takes 0.1 seconds to get up to the maximum. So it then will take 0.1 seconds to get back down to the midpoint. It will take 0.1 seconds to get down to the minimum, and then back up to the midpoint will be another 0.1 seconds. So the period is 0.4 seconds because that's how long it will take to complete one cycle of this movement. What is the amplitude? Well, the full distance between the minimum and the maximum is 10 centimeters. So half of that is the amplitude, or 5 centimeters. 0.4 seconds and 5 centimeters. Let's graph several cycles of the sine wave that models position versus time. At t equals 0, we are going to be at -15. That's our original position. And then at 0.1 seconds, we'll be at our maximum at -10. And then we'll be back at the midpoint, and so on. This is what our sine wave will look like. I'm not very good at drawing this, but you get the idea. Here's a much nicer graph that shows our function h of t equals -15, which is our midline here, plus 5, which is our amplitude, sine 5 pi t. And that has our maximum up here at -10, our minimum at -20, and it has our period of 0.4 seconds.